Welcome to qnawire.
So in this part of the problem, we are given a cylindrical capacitor of length L equals 0.35 meter. So this is the length of the cylindrical capacitor. So let me draw this cylindrical capacitor. So we have the inner core, and then we have the outer shell, like this. The radius of the inner core, let's say, is R1, and the radius of the inner part of the outer core, outer shell, is R2. So R1 is given to be 1.2 mm, and R2 is given to be 2 mm, and the potential between the inner core and the outer shell is given to be 6 volts. And in the first part of the problem, we need to find the linear charge density for this cylindrical capacitor. So we know that for cylindrical capacitor, the potential between the core and the outer shell is given by V equals lambda, the linear charge density, charge per unit length, lambda divided by 2 pi epsilon naught times natural logarithm of R2 by R1. So this is the potential for the cylindrical capacitor, which we have already found in the very few of problems. So using this, we can easily find lambda. So if I rewrite this equation in terms of lambda, so I have lambda equals 2 pi epsilon naught v divided by log of r2 by r1. And if I substitute the values of each and every term, so you know the value of epsilon naught, the voltage is given to be 6 volts divided by natural log of R2 by R1. R2 is given to be 2 divided by 1.2, and if I find this, so my lambda comes out to be 6.53 times 10 raised to negative 10 coulomb per meter. So this is the charge per unit length for this cylindrical capacitor. So this is the answer for the first part of the problem. Now moving ahead to the second part of the problem, where we are required to find the total charge on this capacitor. So the total charge can easily be found to be lambda times L, because lambda is charge per unit length. So charge can be written as lambda times length. So we have already found the lambda, which is 6.53 times 10 raised to negative 10 times the length, which is given to be 0.350 meters. And if you calculate this value comes out to be 2.29 times 10 raised to negative 10 coulomb. So this is the answer for the second part of the problem, the total charge stored in this parallel cylindrical capacitor. Moving to this part C of the problem, where we are asked to find the capacitance of the cylindrical capacitor between the core and the shell. So since capacitance C is given by Q over V, we have already found the charge on the capacitor, the previous part, which is 2.29 times 10 raised to negative 10 coulomb divided by the potential, which is 6 volts. And if you calculate this value, it comes out to be 3.81 times 10 raised to negative 11 farad. So this is the capacitance of this cylindrical capacitor. Now, part D of the problem. In the part D of the problem, we need to find the total energy stored in the cylindrical capacitor. So the total energy stored in terms of the potential is half CV square. Substituting the values of each term here. So we already found the capacitance, which is 3.81 times 10 raised to negative 11 farad times 6 volts square. And if you calculate this value, the energy stored in the capacitor comes out to be 6.85 times 10 raised to negative 10 joules. So this is the energy stored in the capacitor, which is the answer for the final part of the problem. With this, we come to the conclusion. This is the energy stored in the capacitor.